Okay, everybody. So what we're going to be looking at today is section 6.4 in your book, which is Green's theorem. Uh, and our topics are basically going to be this. We're just going to apply the circulation form of Green's theorem, and we're going to apply the flux form of Green's theorem, which we'll learn about those momentarily. Um, so before we do that, let's just get the idea of what is Green's theorem? What are we going to be doing? So the idea is this. So you know that well, you know the fundamental theorem of calculus, right? From Calculus 1. So just think about the fundamental theorem of calculus, right? It's good for you. So just sit there and think about it. Think about the fundamental theorem, builds character. All right, so here it is, right? So you have the integral from a to b of little f of x dx, and that turns out to be f of b minus f of a. And you probably have never thought about it this way, but it's actually a little bit weird here because what you're saying when you write down the fundamental theorem of calculus here is you're saying that um, to evaluate um, an integral over AB, right, you're actually integrating this f of x at all of the points between a and b, right? But somehow, to actually get the number at the end, all you need to know is the b and the a. And that's a little bit weird. So to evaluate an integral over a to b, uh, we only need uh, the boundary of the interval, right? What's the boundary of the interval? The a and the b. Okay. And Green's theorem is a similar idea. So Green's theorem, what Green's theorem does is it relates a uh, line integral over a vector field, line integral of a vector field over a closed um, circle, not necessarily a circle, a closed curve. Okay, let me just say it. Um, so Green's theorem relates a line integral of a vector field over a closed curve to a double integral over the region enclosed by the curve. Now, that's not the actual theorem, that's the idea. Now, why would you care about that? Well, because a lot of times the double integral is going to be easier to calculate than the line integral. Um, so we care because the double integral is often easier to compute than the line integral. Also, you can prove different types of theorems with this. So it's theoretically important, and also it's important just because it lets you calculate more integrals, and that's what we really want to do is calculate more integrals, right? You haven't done enough yet. You just need to keep going until you've evaluated all possible integrals in the entire world. All right. Now, I'm not going to do this quite the way the book does. I mean, mostly we will. But one thing I want to get across early is that there's going to be two forms of Green's theorem. Okay, so two forms of Green's theorem will exist for us in this section. They are what we're going to call the circulation form and the flux form. And the reason that we're going to need these two different forms of Green's theorem is because if you remember the section on line integrals, there was a difference between doing a regular line integral and doing a flux integral, right? One had the r prime and the other one had the n, the normal vector. So those are going to give you two different theorems here because there's two different types of line integrals. So I don't know which one's which, so I'll just pick one, put it down here. So here's the flux form. Let me find the other one. And there's the circulation form. So let's read these, see if we can understand what's going on. The idea is what I said it was, though, right? Remember, the whole idea here is that we take, the whole idea is we relate a line integral to a double integral. All right, so that's what you're going to see in both of these. So what's going on here in the circulation form is you've got, well, first of all, you have a vector field. P and Q are the component functions. They need to have continuous partial derivatives. They need to have continuous partial derivatives because we're actually going to take the derivative of them. So that's why that makes sense. And then here's the relationship. So what we've got going on is that we've got the line integral over a closed curve, right? It says simply connected region with boundary curve C that is piecewise smooth, simple closed curve, oriented counterclockwise. So we actually need that it's counterclockwise as well. And then we'll have this idea here. So what do we have? The line integral over the closed curve, which could also be written this way, is going to be this double integral. So you've got in here the partial derivatives, right? Your original function had a p and a q. So like you can calculate, you throw py, but you can calculate py and you can calculate qx just by taking two partial derivatives. That should be pretty easy. And then you're going to just stick them in this double integral. And so actually applying this is not going to be too hard at all. And this is the theorem. We're not going to prove it, by the way. We are going to do an example at least to show ourselves that it may be true, but we're not actually going to prove this because the proof is hard. Okay, it's not even in your book. I'm not just skipping it because I want to, like I do sometimes, but this one's actually not even in your book. Now let's look at the flux form. So conditions should be similar. D is open, simply connected region with boundary curve C that's smooth, simple closed curve, oriented counterclockwise. Exactly the same. F is P, comma Q, vector field with component functions that have continuous partial derivatives. And then here's the formula. And so it's different because this one's the F dot dr type integral. And if you look here, it's qx minus py. And here it's the normal type. And there's a couple differences here. First of all, notice that the qx is now px, the py is now qy, and also there's a minus sign difference. Now that probably, doesn't surprise you too much because remember that the difference, I'm just going to say, recall the difference between the regular line integral and the flux line integral. I'm going to say circulation, even though we didn't use that too much. Circulation and flux line integrals, right? So the circulation type was like this. The f dot dr type, when you actually go to do the integral, was an integral of, what was it? A to b, and then you have your f of r, and then you have your dot r prime. But instead of writing it that way, I'm going to write your r prime. Well, I lied. I'm going to write it this way: r prime, um, and then your dt, right? And we didn't write it this way, but your r prime, if you write it as a vector, was x prime comma y prime, right? Like that. And your other line integral type was the integral of f. Um, yeah, they didn't use the equivalent definitions, right? Like I could have wrote f dot t ds there, but I didn't. I guess now I did. I don't want it though. The other form of the line integral or was f dot in uh, ds, and that one, when you actually get around to doing it, was a to b f of r, and it wasn't dot r prime this time. It was dot with a normal vector dt, and I believe if you go and you check the notes, there was which way was it? I think the normal, did they put the negative on the first component? I think um, it's in the formula that they gave you. I gave you two formulas because I said the negative could be on either one depending on what you want to do. Yeah, they use uh no they don't. Where is it? Oh, come on. Oh, there it is. Yeah, they use this. So they use y prime comma negative x prime dt. So that explains the difference in what's going on here. Um, so these components are here, these components are switched, and also there's an extra minus sign. And so uh, that's why the x is on the q here, here the x is on the p, and then also there's an extra, this one was negative over here, the one with the p was negative, but the one with the p is actually positive down here. So just, don't be surprised by a couple things being swapped around in the two forms, because a couple things are swapped around in the forms of the regular line integrals too. Okay, so that's the first thing I want to say about that. Second thing is we're not proving these. We're just going to do some examples. Let's see if I can find one that's not going to be too hard to integrate. Um, hold on here. Triangle. Uh, yikes. Okay, well, maybe we'll do it. Okay, we're gonna do it. This is gonna be our kind of theory, quote unquote, theory. So let's go ahead and get started. So we won't do the proof. But let's do a certain integral two different ways. Okay. So let's see if I have one that we can do. Yeah. Okay, we'll just do it. So this is example from the book 6.38. And I'm going to, they say this, they say calculate the line integral. Circle indicates it's a closed curve. X cubed, nope, x squared y dx plus y minus 3 dy, where c is the rectangle. And the reason I was, wishy-washy on this is that there's four pieces to the boundary here. 1, 1, 4, 1, 4, 5, 1, 5, and oriented counterclockwise. Okay. And so the first thing I'm going to do is I'm going to not use Green's theorem. We should use Green's theorem. Okay. That's the whole point. We're in the Green's theorem section. So, oh, look, I'm saying Green's theorem and I'm writing it in green. So we could use Green's theorem, but we're going to do it the old way first. Okay. So let's look at our region. Um, so our region, we go from 1, 1, there it is, 4, 1. I'm going to change my, no, it's fine actually. 1, 1, 2, 3, 4, 4, 1, 4, 5, 1, 2, 3, 4, 5, 1, 5 here. So there is your line integral or your C. So this could be, and also it goes this way, right? Counterclockwise. And there's four pieces to this boundary. So we would have to actually number it C1, C2, C3, C4. Now, it doesn't matter which piece is which, but that's what we would have to do if we were going to do this line integral, right? Now, I could parameterize each piece, and actually I will right now because we're trying to do this relatively quickly. So for my parameterization for C1, I could use R of t. I'm just going to write R. And what I can see for C1 is that the x value is just stuck at 4. Is that right? Yeah. The x value is just 4. The y value, I said 4, I wrote x. The x value is 4. The y value is changing from 1 up to 5, right? Yeah, because we're going from, nope, not that point. We're going from 4 comma 1 to 4 comma 5. So we could put like a t there, and then you could just say t goes from 1 to 5, right? So that's pretty simple parameterization. For C2, we would have a different R. The way I drew it, again, is down here. In this case, the y value is just 1, and the x value could be t, and then t has to go from 1 to 4, I think. And on C3, R could just be, looks like the x value is stuck at 1, the y value could be t, and then the t value, and this is where you have to pay a little bit of attention to make sure you get the direction right. So actually t would normally, like if it's going from 5 down to 1, we would like to put 1 here and 5 here, right? But the problem with that is if t goes from 1 to 5, then that would be from 1 up to 5, and we want it to go the other way around. So I actually have to change this parameterization a little bit, put like a negative there. That way it starts. Wait, no, that won't work. It will work, but not that easy. We'll have to do something like this. We'll have to do like 5 minus t. And then this would be not this. T could start at 0. That way it's starting up here at 5. And then t goes up to 4. And 5 minus 4 is 1. So a little bit tricky there, but we could use that. for our C3. And then for C4, it's going to be similar. So for C4, the way I've got it drawn, the Y value is stuck at 5. And the X value, it needs to go from 1, 2, 3, 4, 4 down to 1. So again, you'll do like 4 minus t, and then t can just go from 0, and you'll be starting at 4 here. And if we go up to 3, then we'll end at 3, which is 4 minus 1. Sorry, 4 minus 3, which is 1, 1 comma 5, which is right there. So a little bit tricky for those that are kind of going the opposite direction from the natural direction, but there we go. We have those. Now, once you have those, if you want to do the line integral over C here, then we would have to, I'm also going to just draw a little bit of the vector field in here. There's a picture in the book. I have it saved. I can show you, but I'm just not going to do that right now. Okay, it doesn't really matter what it looks like. But you have a vector field on here. And what we're trying to do is we are trying to calculate the line integral that's given. Okay. So how would we do that? If we were going to try to do this line integral, we actually have to split it up into 4 line integrals, right? So the integral over C of, I'm just going to write f right here. F dot dr, I'll say. You have to do the integral over C1, f dot dr, plus the integral over C2, f dot dr, integral over C3, f dot dr, integral of f dot dr over C4, right? 4 pieces, so we have to do 4 line integrals here. Okay, and the circle there on the integral symbol just means it's a closed circle. Okay, now you might think like, oh wait, isn't that 0? And that's only 0 if you're looking at conservative vector fields. We have no reason to believe this is a conservative vector field at the moment. Okay, so let's do this actually. So we'll do 4 pieces, do each of the 4 pieces, and we'll have to add the results. So let's start the first one. So line integral over C1 of f, actually let me just, what is our f? x squared y dx, y minus 3 dy. Okay, and we're doing C1. So for C1, like this is your R, right? So what you're going to do is just make sure you understand, like the x is 4 and the y is t, right? That means that, you know, dx dt is 0. Okay, which means that dx is 0 dt. Okay, and for the y, dy dt is 1, which would mean that dy is equal to dt. So then if you go and you set up this integral here, you're going to have the integral from your limits of integration here are going to be 1 and 5 for C1. So 1 and 5. You're going to plug your 4 and your t in here for everything. So we have 4 squared t dx, which is 0 dt, plus y minus 3, y is t, so t minus 3 dy, and dy is just dt. So because that's 0, this is actually just going to drop off. We're just going to have the integral from 1 to 5 of just t minus 3 dt, which is going to be t squared over 2 minus 3t from 1 to 5. Okay, and then we're just going to get an answer there. But we may as well start doing this now because I don't want to integrate all four of these, right? I'll set up the integral, but I'm not going to integrate them all myself here. So let's go Wolfram and get that all ready to go. And I'll just type it in here. So I'll just integrate t minus 3 dt from 1 to 5. Oh, 0. Weird. Okay. Oh, actually, yeah, it makes sense, actually. Um, it does make sense. You can't really tell on my picture, but if I had drawn this better, like the vector field is slanted up and to the right here, and down here it's slanted down and to the right. And so they're sort of canceling each other out, I guess. Um, all right. Anyway, so that one was 0. We could have just plugged in the numbers and gotten that quicker, I guess. Um, but we didn't. The next integral we would have to do would be for C2. So integral over C2, x squared y dx plus y minus 3 dy. Um, just like the other one, we're going to need to know what is our r. R is t comma 1. So x is t, y is 1. So that's going to tell me like my x prime is 1, my y prime is 0. Um, you can put a dt on that if you want. Except you kind of have a choice actually. Like if you write this x prime 1, y prime 0, then you'd feel those, uh, you could write that, but you should write like dx equals dt in that case, and dy is going to be, 0 dt in that case. So fill them in. What's our limits of integration? 1 and 4 for C2. So 1 and 4 for C2. X squared is t squared, y is 1. Dx is just dt plus y minus 3, that's 1 minus 3, but then dy is 0 dt. So we actually just get the integral 1 to 4 t squared dt. I'm so lazy that I'm actually going to just type it in. T squared dt 1 to 4, 21. So we got 21 from this one, 0 from this one. Move on, let's do C3. So the integral over C3, I was using green for the to help keep track of when I was switching integrals. Integral over C3, x squared y dx plus y minus 3 dy. What parameterization are we using for C3? 1 and 5 minus t, like that. So dx is going to be it's going to be 0 dt. Make it drop off. Dy is going to be negative dt, it looks like. Uh, so our integral here, I don't know the limits of integration yet, but x is going to be 1 squared, 5 minus t, dx is 0 dt, plus y minus 3 is 5 minus t minus 3, dy, which is negative dt. Limits of integration, 0 and 4 for C3. 0 and 4. 0 and 4. So we get the integral from 0 to 4 of, it looks like 5 minus 3 is going to be 2. So 2 minus t, and then negative dt, which I'll do that way. And hopefully I didn't screw that up. Let's go over here. We have, we're integrating negative 2 plus t dt from 0 to 4. This one is 0. For the same reason the other one was 0, it's due to the symmetry up here and down here. Like this is still a little bit up to the right, and this is still a little bit down and to the right, even though my drawing doesn't make it look that way. And so when you're trying to figure out how much of the fluid is flowing in this direction, like when you add it all up, it adds up to 0. Okay, so we have that last piece, C4. X squared y dx plus y minus 3 dy. C4 is up here somewhere. 4 minus t comma 5. X is 4 minus t, y is 5. So that's not bad. The dx is going to be negative dt, and the dy is going to be 0 dt. Plug it all in. What are our limits of integration? 0 and 3. So we're going to have 0 and 3. Plug this all in. 4 minus t squared for x. Y is 5. Dx is negative dt plus y, which is 5 minus 3, which is 2, dy dt, which is 0 dt. So this one drops off. So we have an integral from 0 to 3. Put a 5 out there. 4 minus t squared negative 5 dt. Okay, so let's do this integral. Probably type in the one above it just because it looks nicer. 4 minus t squared times 5, squared times times 5 dt. Oh, that's actually should be negative dt. So I'll put the negative out front. From 0 to 3, I guess. Negative 105. Okay, so we did those. And then if we add them up, so the overall integral over c, I'm just going to write f because I don't want to write it again. What did we get? Well, we had the negative 105. We have a 0. I know we have another 0. And then we had something else and a 21. So you add that up, negative 105 plus 21. And we get negative 84. Okay, so that's my actual answer to the question, final answer. That's my line integral. Now, that was slow because we had to parameterize 4 pieces of the boundary. So even though the individual integrals were very quick individually, we still had 4 of them to do, and that made it take a long time, right? Now let's see what Green's theorem would say about this, though. What does Green's theorem say? Well, let's find out. Okay, so what does Green's theorem actually say? So it says this, right? Normally, it says that an integral over c of f dot dr, provided that those individual pieces meet some definition. So if that is integral over c of p dx plus q dy, right? So one's p, one's q. that is going to be the double integral over d of qx minus py dA. Okay, so that's what Green's theorem says. Now, if we take a look at this, I'm just stealing my picture. Oops, I actually stole it. Duplicate it. Close enough. So what's going on here is the D is just the inside here. So this is the D that they're talking about for that double integral. That's not easy to see either. Okay, so that's D, right? And so let's figure this out. So if we're looking at our original integral here as well, our original integral, which is somewhere way up here. Okay, duplicate, bring it down. Okay, so here is our integral. So what's the P, what's the Q, what's going on, right? So first of all, that must be P because it's multiplied by the dx, that's multiplied by the dx. That means this must be Q, right? So px, that's the partial, sorry, we don't need px, we need py. Py, that's the partial derivative of p with respect to y. That's going to be x squared, right? I mean, you have to calculate this. I should show the calculation. So that's the partial with respect to y of x squared y, which is x squared. And qx, that's the partial with respect to x of y minus 3, which is going to be 0. Right? So you calculate those. So let me write, we should write our steps here. Step 1, find py and qx. Our second step is going to be simply to set up our integral, right? Set up the integral. And I'm specifically talking about the double integral now. Okay, we need to set this up. So we know that the integral is going to be equal to the double integral over d. It is qx minus py. Did I get the right one? I must have, right? Yeah. Qx minus py dA is simply going to be a double integral. We'll fill in those limits in a second. The qx is 0 minus the py is x squared. The dA is either whatever one we want to do first, the x or the y. Let's do the x first, right? So let's just say dx. X could go, well, what's x? Remember, this was 1, this was 4, this was 1, this was 5. So it's just a box. So the limits for x are simply going to be 1 and 4 for that box. And the limits for y are going to be 1 and 5. So this is a very quick integral or very easy double integral, right? We're going to integrate. So we have integral 1, 5, integral 1 to 4. This is just negative x squared dx dy. So let's do it. You would find an antiderivative, so negative x cubed over 3 from 1 to 4. Then that would be put in the 4. Negative 4 cubed over 3 minus negative 1 cubed over 3 dy. So this is negative 64 over 3 minus a minus is a plus 1 over 3 dy. So that looks like integral, it looks like negative 63 over 3 dy. But isn't that I mean, wait, what's 63 over 3? 21. So that's integral from 1 to 5 of negative 21 dy, which is negative 21y. That's the antiderivative from 1 to 5. So you get negative 21 times 5 minus negative 21 times 1. So 21 times 5 is 105. So this is negative 105 plus 21, which is negative 84. The same answer that we got up here somewhere. Yeah, final answer, negative 84. So I showed all the steps for calculating an integral, which I did not do for the line integrals. But point is that we did it. This is clearly less work, and we got the same answer either way. So we didn't do a proof, but at least we did the integral twice, and we got the same answer both times. Okay, so that's all you're going to get out of me as far as that goes. And that's how you apply Green's theorem. Is really you're just going to make sure that your function actually meets the requirements in terms of closed curve, continuous partial derivatives, that kind of thing. And then if it does, then Green's theorem applies, and you apply it. The end. Let's see if I can do a problem here. See a flux type integral. You could do that. Actually, yeah, let's just do this one. This is going to be straight off of the homework. Like literally, this is a homework question that you have. Example, let C be the triangle with vertices 0, 0, 1, 0, 0, 6, oriented counterclockwise. Remember that was part of the definition. Let F equal, looking a little complicated here, 6x minus 2y cubed plus 3, okay, plus 3y squared, comma, 8x cubed minus 6x squared minus 5y minus 4. Yikes. Now, it's not as bad as it seems like, because when you do partial derivatives, some of these terms drop off. That's another nice thing about it. And they say calculate flux across F. No, flux across C. Flux of F across C. Okay. So, first thing to do is to, see if we're going to be able to apply this. So I didn't add that as a step before, but we can talk about it now, right? So just double check that, C is going to be a simple closed curve. And, yeah, that's the main thing. Simple closed curve. That the partial derivatives of the functions in F, the partials of the component functions of F are going to exist and be continuous. And what other conditions do we have? Okay, open, simply connected region. Yeah, so the region is going to be inside that triangle. That's fine. C is piecewise smooth, simple closed curve. So oriented counterclockwise. The vector field of continuous partial derivatives. Then we have the theorem. Okay, so everything seems to be fine here. everything seems fine. So move on to the next thing we need to do, which is going to be there's two forms of Green's theorem. So we need to consider whether we're doing the flux form or the circulation form. Um, choose correct form of Green's theorem, right? We have circulation, which is the normal kind, or flux. We have flux because they said calculate flux. So we have flux. And then we should just be able to get into it. So Green's theorem, the formula, right? Uh, this one. So the flux across C, it's going to be double integral px qy. So that's opposite px qy, and it's a plus sign. Px qy, and it's a plus sign. So Green's theorem is going to be the line integral over C of f dot n ds is a double integral over d. D is inside of C. Um, what is it? Pdx plus qdy. Oh, that's how it was. Uh, wait, what? No, px. Sorry, brain did bad. Px plus qy dA. Okay, there we go. I don't know what just happened. Okay, so let me where are we? Yeah. All right, so we're good. So what are we going to need? So we've got so we can set up our integral is what we need to do. All right. So what are we going to need? First of all, we're going to need to know what the region looks like. So let's start there. Which there it is. Okay. So we have a triangle with vertices 0, 0, they said. 1, 0, they said. I'll put that for here. Nope, because of the space. That makes it hard. So we have 0, 0. We have 1, 0. And then finally we have 0, 6 here. All right. So this is our curve is like this, right? Oriented counterclockwise. And then our region that we're going to be dealing with is on the inside. So the inside is where D is, right? So curve on the outside, D is the middle. Okay, so that's our thing. Now, if we were going to come up, we are going to have to set up this integral. Then this is not going to be a difficult double integral to set up, but you are going to need to know the equation of this piece of the boundary, right? So you'd have to figure out the equation here for this line. It would be something like this, right? So that would be y equals, the y-intercept is 6, and then the slope is such that it's down 6 over 1. So that's a slope of negative 6. I was going to put a t, but you know, that way, right? So 6 minus 6x. That way when you put in a 1, you get 0. Okay, so you're going to need to know that. Now, having done that, what's the p, what's the q, and so on. So the p, remember, is going to be the first thing here. So p is 6x 6x minus 2y cubed plus 3y squared. And we need px, right, for that. So px is just the partial with respect to x, 6. Notice that they kind of rigged it so that it looks kind of complicated, but then when you actually do the partial derivatives, it becomes simpler. The q, which you'd have to scroll up to read again, but I can read it on my screen, so I'm just going to see it, write it. 8x cubed minus 6x squared minus 3y squared minus 5y minus 4. And we need qy. So we need the partial with respect to y. There's no y's, there's no y's, there's two y's. So the derivative of negative 3y squared is going to be negative 6y. And the derivative of negative 5y is going to be negative 5. Okay? So we're able to use Green's theorem then, which is going to say the integral over c of f dot n ds is going to be the double integral over d. What was it? It was px plus qy dA. That's all, right? So if we put in everything that we've got the double integral, which we'll have to come up with limits. The px is 6 plus qy, which is negative 6y minus 5, then dA. We'll do dy dx. And the reason we're going to use dy dx is because once we have the equation of that line there, you're able to say that our d here, pick a different color, our d here is the set of all x comma y such that the x can just go 0 to 1, and the y value can go from 0 up to that curve. So you would go 0 less than x less than 6 minus 6x, like that. So then your limits of integration are pretty easy. You just go, y goes from 0 to 6 minus 6x, and then the x value just goes 0 to 1. So that's not a super tough integral to set up. I guess we can do one more line of work before we integrate. 0 to 1, 0 to 6 minus 6x. All you would do is just 6 and the negative 5 are just going to add up to 1. So you're just going to have negative 6y plus 1 dy dx. So that's your setup. It's not that bad. I mean, you had to set up a double integral, but it was a pretty simple double integral. And now we should just be able to finish this problem up by integrating, though. Integrate. So yeah, we're just gonna solve this integral, which actually for time we're not going to solve. We are going to make a computer do it. So here's how I like to do these. You've seen this a lot. I like to type in the entire middle integral and get an answer. So I would be doing negative 6y plus 1 dy, and then I go from 0, I should say y equals 0 to y equals 6 minus 6x. I think that'll give me a good chance of having it do the right thing. Double check that it did the right thing, and it says, here's my work. So I get negative 6, 18x squared minus 35x plus 17. Okay, and then I need to integrate that from 0 to 1. So I know that what I can do is I can just click on that answer. It brings it up there. Notice it changed the order that it wrote stuff. That's weird. And then I can just say integrate again. Integrate again. This time it is a dx integral. And then we go from 0 to 1. And I get negative 33. And I'm done. Now, of course, I made that easy by letting the computer do the integrals, but you could make it. You can do the integrals yourself if you like doing integrals, and that's the flux. Okay, so that is the flux across C. Okay, so we did a double integral, but we calculated flux because Green's theorem lets us do that. Okay, so that's really the main idea there, but of Green's theorem is that we replace line integrals with double integrals. Occasionally, you can find a function where you can have problems where you would like to do polar coordinates, that kind of thing. Maybe we'll do one of those. Again, this is off the homework. Let's see. Be a circle with a radius 4, uh, centered at the origin, traced counterclockwise. If they ever say clockwise, by the way, you know that the direction will change the sign to the opposite sign. So you would have to just do Green's theorem and then add a minus sign. All right, C is a circle, radius 4, centered at the origin, traced counterclockwise. F is 10x minus 5y squared minus 7, comma, negative 6x squared plus 10y plus 6, and we want to calculate flux cross C. All right, so same as before, we want to just check the conditions, right? Right, so closed, simple C. Yes. F with continuous derivatives. Yes, etc. Right? I'm just mentioning that because they might ask you why it's not allowed to be applied or something like that at some point. So just at least think about the fact that there are conditions that you have to satisfy before Green's theorem applies. Um, what form of Green's theorem is it? We want the flux form because there's two. And then we should set up our integral. So we know that the whole point is that line integral over C of f dot in ds, that's the flux integral, is going to be the integral over d of, what was it? Flux, so it's px plus qy, right? dA, the same kind as we just did. Px plus qy dA. And yeah, so there we go. Now, in order to do this, we're going to need the px and the qy. So let's just do those. So p, q, what's p, what's q? So the p is 10x minus 5y squared minus 7. The q is negative 6x squared plus 10y plus 6. So we should be able to find those partials pretty easy. We need px, which is going to be 10. We need qy, so partial of this with respect to y, that's just going to be also 10, right? Well, that's easy, right? They make it look more complicated than it is because when you take those partial derivatives, stuff drops off. So you find your px and your qy. So now we need the integral is going to be, that's sort of an integral symbol. So now we have the integral over c of f dot in ds is double integral over d. The px is 10, the qy is 10, the dA is just dA. And we know that our region, right, is the inside of this circle, and that's radius 4. So just use polar coordinates. That's an easy integral, right? We can still combine what we know. We can still do polar coordinates for Green's theorem here. So when you're integrating over a circle in or a disk technically in polar coordinates, we know that we're just going to have r go from 0 to 4 here because the radius is 4, and we know that we're going to go all the way around the circle, which is 0 to 2 pi, and then you got your 20, and then your dA is r dr d theta, right? That's your dA. That made it look like I was dividing by dA. Okay, so polar coordinates is going to be really easy there, and then we should just be able to integrate this. No big deal. We won't even need a computer. So I could take the 20 out, and I have integral from 4, 0 to 2 pi, just r dr d theta. So we have 20 integral from 0 to 2 pi. Antiderivative of r dr, r squared over 2, 0 to 4, d theta. So we have 20 integral from 0 to 2 pi. Plug in the 0, sorry, plug in the 4. 4 squared over 2 minus 0 squared over 2, d theta. Work that out. 16 over 8 is, 16 over 2 is 8. So just 8 d theta. Take that 8 out, you have 160 integral from 0 to 2 pi of d theta, which is 160. Integral of d theta is theta from 0 to 2 pi. 160 2 pi minus 0. 320 pi. That is flux across C. And that's your answer. Okay, so we've done a few of these now. I think you get the point. Point is you are going to be given a line integral. You turn it into a double integral, and then you integrate. What? Oh, that's stupid. Okay. There is one more thing that we need to talk about here, which is what to do if there's a hole. I thought that I did not assign those, but sadly, we did. All right. Okay. So regions with holes. Okay. So what we have is that with what we have so far, you couldn't apply Green's theorem to a shape like this. Um, so you couldn't apply it to a curve or a region with a hole, um, like this. So the most common one that they give us is one like this, where they have, they say like, so I guess this would be C, and the inside there, that would be the region D. And okay, so that's not a situation that we would be able to handle, right? Like you have like the integral over um, C. Actually, the way they like to do it is they don't call that C. What they like to do is they like to call the inside D, and then they say you're doing a line integral over this symbol, and that means the boundary of D is what they mean. Um, and then I could just say like PDX plus QDY or something. Uh, so this is just a note here. Boundary of region D. So that's actually the curve. Okay, that's like the curve on the outside is the boundary, but also the curve on the inside. So both of them are curves. Okay, and so in order to handle that case, we need a little bit more terminology, and basically you need to know the idea of orientation here. So positive versus negative orientation. So yeah, okay. So the idea is this. Green's theorem didn't apply because the region has a hole, right? Sad face. But you can split the region. So you could split the region like this. So what you do is you take that shape that we've got up there and you split it into two half donuts, right? So you can split that region into a shape like this, and then your C can just be like this, and it has to go around the inside there like that. And then your C on the other one, you have another C. Well, it was going like that, right? Because the original one was going counterclockwise. And then in here, it'd be like that, and then that, and then like that, and then that way, and then that way, right? So you can split it like this. And then Green's theorem would apply in each of those, right? So if I go got that one up there with, let's say, what do they call it? No, they didn't. Um, I'll just say C1. Well, maybe with a color that actually writes, C1. And then the other one could be with a color that actually writes, C2. So you can split it up that way. And then in each of the two shaded regions separately, it is Green's theorem would apply. Okay. And then what you're actually able to do is if you, um, let's see here. I don't like their notation. Okay. So you can split the region like this and then apply Green's theorem. That's the idea. But then like the specifics are going to be this. So there's a little bit of like terminology here. Um, so let D be a region and C be a component of the boundary, right? So like the boundary might be in two pieces. So D could have a hole. Boundary could be in two pieces. Okay. So that's the situation that we have like above, where the boundary actually has an inside piece, this circle, and an outside piece, the other circle, right? The boundary is the edge. So there's two edges, one down here, one up here. Okay. Um, Positively oriented is if you're traveling in the direction of the curve, the region is always on your left. So positive orientation. Uh, if you travel in the direction of travel, so if you travel along C, um, and the region is always to your left, then C is positively oriented. Okay, so negative would be the opposite. If you travel along C and the region D is always to your right, then C is negatively oriented. Right. And then just kind of a note here is for the ones that we've already seen, right? Note, if there are no holes, counterclockwise is positively oriented. That's why we were choosing it. Just think about it. If you have a shape and you're going that way, then if you're traveling along that curve, then the region is always on the left, right? If you're traveling this way, left is over here, right is over here. So that's positively oriented. So counterclockwise is positive orientation. Okay. So then what you're going to do for the case on a region with holes is this. So here's kind of the application. Um, so put our formula here. All right. Assume uh, the region, or sorry, the boundary of D um, oriented so that the um, outer boundary has a positive orientation. And the inner boundary, the holes, right? So those are any holes, have negative orientation. Then what happens is that when we split it the way we showed it here, um, we get positively oriented. Each of these shapes is positively oriented. So let me show you that. Duplicate this. Right. So here's the situation that's going on. So you're starting with this. Okay. And you're starting with the outside should be going counterclockwise, right? And then the inner boundary should actually be going the opposite direction. And so this is positive orientation and this is negative orientation, right? This one's positive because if you're traveling this way, the left side is here, right? This is negative orientation because if you're traveling here, then, oh, oops. Something happened here. The inner holes given a negative orientation of the outer boundary. That's, wait, that's not true. Their definition is wrong. Yeah, their definition is wrong here though. Hold on, I'll show you. 6.4. Yeah. So here's the picture. So this is what they want to happen, which is what I'm drawing. So that's correct. However, if you look at, I can't really point, can I? I'll have to take this picture. Um, Okay, so you see the problem here, right? If you're right here, then if you're traveling in the direction of travel this way, left is on the inside. And on this one, if you're traveling this way, then the region D is also on your left. So this is also positive orientation. But they say that uh, it's not. So they must be considering like this boundary here, like if you took it out of the thing and said, if you were looking at this and this was your region, then this is negative orientation because the region is on the right of the direction of travel. However, the way that they've drawn it, with this going this way and this going this way, then left is inside and this left is inside, right? So that's not actually negatively oriented um, with respect to the region D. So I don't really. All right. It doesn't really matter here, but that's the issue. I don't really like what they're doing there with their terminology is what the punchline there is. But anyway, I've got the picture there that matches it. And what they're going to do here is they're going to say, just given this, they say then this is the situation. They say the integral over the boundary of D of f dot dr, you should be able to split that up into the integral over the boundary of d1, um, right, this one, of f dot dr plus the boundary of d2 f dot dr. And the reason that's going to be the case that you can do that is because this part of the line integral here and this part of the line integral here are just going to cancel each other out. So like um, these pieces cancel out when you do the line integral. And that's why you're able to say that this is true. Because if you think about it, right, if you're trying to do the line integral over just this shape and this shape, then there shouldn't be these horizontal lines, right? But the point is that you added one going to the right and one going to the left, and they cancel each other out. One going to the right, one going to the left, and they cancel each other out. Okay, so this much is true. And then once you have this, then each of these can be done with Green's theorem, which would be the double integral over d1, which is the top shape, of qx minus py, that's just Green's theorem, dA, plus the double integral over d2, qx minus py dA. And then you realize that these two these two double integrals just add up to the double integral over the original shape. And so technically what happens is that you can just apply Green's theorem like normal, as long as the boundary is oriented the way they say. So that's the punchline. So let me write that. As long as D is oriented, um, the way it's shown here, right? Then the line integral over C, or sorry, the boundary of D is how they're saying it. The boundary of D of f dot, I'll just say pdx, plus qdy, I guess, is equal to the double integral over D of qx minus py dA. So the point is of all that is that the orientation there is what's going to matter. Um, yeah, so you have to pay attention to it. So you can apply Green's theorem as long as it's oriented the way they say it's supposed to be oriented. That's the punchline. So let me just set one of these up. Well, we're not going to do it because it took so long to talk about that. So example, they say calculate double integral over the boundary of D, 6x cubed minus 7x squared plus 3 dx plus negative 2x minus 10y squared plus 7y plus 3 dy, where D is 3 less than r less than 6, theta in between 0 and 2 pi. And then they say, you may assume that the inner hole of boundary D has negative orientation and outer boundary has positive orientation. And so that's that's what they said were the requirements. Okay, so they're telling you that it's oriented the way that they want it oriented for doing this problem. So like R is supposed to be between 3 and 6. So you got an inside hole, you got an outside hole, not out, not, and the region is in between. That's the D. And this one should go this way, and this one should go this way. Okay, so that's what they want. So, know what that looks like and know what they call it. They're saying the outside has positive orientation and the inside has negative orientation. Okay, so we know already how to do this. This is going to be pretty easy, right? So I'm not going to do everything in as much detail. We have P 6x cubed minus 7x squared plus 3. So P sub what? Well, formula's up here. We're going to need Py because this is not flux, right? This is not flux. So we're going to need Py instead of Px, which is 0, I guess. There's no no y. All right. Now the q, that's going to be the negative 2x minus 10y squared plus 7y plus 3. We're going to need q sub x, which is negative 2. So that's nice. So we go to set up our integral. Make sure we understand that it's not flux, right? It's circulation, not flux. Okay, so we know we should be setting up the integral over, in this case, D, double integral over D, and it should be the one that we have here, qx minus py dA. So again, that's going to be a really easy integral to set up. So the qx is -2. The py is 0. So we just have -2 minus 0. The dA we may as well do in polar coordinates. So we should do r dr d theta. And then your region D here, the r is going 3 to 6 because this is 3 and this is 6. And then your theta 0 to 2 pi. So integrating over that kind of shape is easy in polar. Okay, so this is the integral that you have to do. And, this is really not going to be worth our time to do. I'm just going to write down the answer. You can just work through it and you will get -54, which I guess I'll say, pretend we did another step there. Integrate. -54. Okay, so I think that's going to be it for here. I'm just going to click a little bit through here. Why are there so many questions in this section, though? You should probably use a computer to help you get through these integrals in a reasonable time. Because you have to do a problem like this one, 5 times in a row. They don't have a lot of different problem types, but they're just giving a lot of problems. 69%, 75 now. All right, I want to look at the last topic here. Oh, okay. Dang. Last topic. We're already so long in here. Wait. Where's the problem? Okay. So I'm not going to derive this, but I'm just going to write it. Area. Okay, so here's the deal. So if you've got this kind of shape, okay, so we got this. Just put an arrow on there. Shade the area on the inside. So we're going to have the setup that we're used to. We're going to call the curve C. We're going to call the inside D. We don't have to refer to the boundary, I don't think. Okay. So the curve is C, and then the inside is D. Right? That makes sense. Okay. So your two formulas here for calculating the area of D are as follows. So the area of D can be computed uh, what? Okay. The integral over C of x dy. And so there's a thing in the book where they teach you to do that, but I think this is all we're going to need, okay? So we could do that. Yeah, I think that's it. So let's, there's another formula they give you that I don't think we use, but, or the integral over C of 1/2 the integral over C of -y dx plus x dy, which would mean that you would be able to also just integrate negative y dx and also get the same answer. And I'm not going to derive that. I'm just going to state it, and then we'll do one example of it. So let's pick this off the homework. Um, use Green's theorem, which we haven't, I didn't say there was any Green's theorem there, but use Green's theorem to find the area enclosed by the curve with parameterization r of t equals 5 sine t cos t, comma 3 sine t for t in between 0 and pi. Okay, and so normally, well, let's look at this picture, but want to make sure, try to clear this up. No, normally you calculate areas with double integrals, right? So normally you calculate area with a double integral. Okay, what we're doing is the opposite. But if you use Green's theorem in the opposite direction that we've been using it, right? Because we've been using line integral to double integral. Now you could use double to line integral, right? That's the opposite direction of normal. Then we could calculate an area with a line integral. And the line integral is the one that I already wrote down. It's going to be area equals line integral over C of, what did we say, boundary of D? No, did they just say C? Area enclosed by C. Um, just x dy. Okay, so that's all we're doing. And so um, again, if a double integral is related to a line integral, then area is related to a line integral, and this is how it's related, and I'm not proving it. Having done that, this is not going to be hard to do at all, right? Because this is a line integral. So you would simply, so if the area is the line integral over C of x dy, and you know you have x is given as 5 sine t cos t, right? And you have y as 3 sine t, then it's not going to be hard to find the dy here, right? Dy, I guess dy dt, is going to be 3 cosine t dt. You don't need dx, and we can just substitute this in. Sub in to formula. So really we're just using this formula here. So we have the area is the line integral. We're going to have x. X is 5 sine t cos t. The dy is 3 cos t dt. And then your limits of integration are simply going to be whatever you had for your curve, which are 0 and pi. So you get this integral, and this integral we can do without even really knowing what the shape looks like. So what do we get? We have 15 on the outside, integral from 0 to pi, cosine squared t sine t dt. So you'd have to do that integral. You'd have to do like u is cos t du is negative sine d dt. So you end up with 15 integral u squared du with a negative. But then if you put in a pi into here, cos pi is -1. And if you put a 0 into cos t, cos 0 is 1. So you end up with 1. I don't like that, so I'm going to flip that, add another negative sign to make it -1 to 1 squared du. And this integral is going to be easy. Compute. So you end up with 15 u cubed over 3 from -1 to 1. So 15, 1 cubed over 3 minus minus, actually just minus -1 cubed over 3, which is 15, and then 1/3 plus 1/3, which is 2/3. So it's 15 over 3 is 5. What? 15 times 2/3, 10. So 10. And hopefully that's right. I think it is. Um, the shape, by the way, I'll draw the picture for you, which you did not need to know the shape at all. You just had to know that, the problem they were giving you was proper in terms of that's not supposed to be symmetric. So it's like this. It has like kind of a sharp corner there. Uh, and so that's the area that we were calculating. Area. Okay, so it's a complicated shape. You never would have been able to calculate the area of a shape like that without doing this. I mean, you could have actually, because I mean, you have another formula for calculating areas in polar coordinates, but um, there we go. Uh, I guess last thing, I'm not going to do any examples of these, but I'm just going to remind you or show you, I guess, I don't know which, um, work. Just recall um, an object moves along C in a force field F. Then the work required to move the object is given by work equals integral over C of F dot dr. So it's the type of line integral we have already done. Um, so what we could say is that using Green's theorem, that would be the double integral over d, qx minus py dA, right? Where that's f is p comma q, etc. Right. So there's not really anything to do there. Um, it's just reminding you that you can do a line integral to calculate work. So if you have a problem involving work, you can use Green's theorem on it, just like you could for any line integral. And it's a circulation type, not flux type. Okay, and I'm not going to do an example of those, but it's another just set up the integral, but do it with Green's theorem. Uh, yeah, so that's it. Okay, so that's it for this lecture. It's not so bad, I don't think. And yeah, I will talk to you guys later.